Hi there, my name is Philip Kuznetsov. For my computational photography final, I re-implemented the paper Creative Adversarial Networks. The premise of Creative Adversarial Networks, or CAN for short, is that the authors modify the GAN objective to not only produce new pieces of art from the art dataset trained on, but also to try to deviate from the styles seen within this artwork while still producing realistic looking images. This paper came out a few months ago, but the authors never released the code. This sucked because I really wanted to play around with it, but it opened up the opportunity for a new side project, so I'm not that mad. And here's a result from the trained model. This is an interpolation over the input space of the generator network. Basically, I sample 16 random vectors, interpolate between these random vectors, and then feed each subsequent random vector into the neural network, which creates this smooth transition between many different pieces of supposed art, at least as defined by the network. To motivate this work, the author focuses on Colin Martindale's hypothesis that, quote, creative artists try to increase the arousal potential of their art to push against habituation. However, this increase has to be minimal to avoid negative reaction by the observers, end quote. This description lends itself nicely to an optimization formulation, which could then be captured via loss functions. To push against habituation, creative adversarial networks have two additional objectives on top of the generative adversarial network formulation. The discriminator tries to classify images as belonging to a set of styles, while the generator tries to create a realistic looking image while making sure that it doesn't fall into any one of those classes. This last objective, the additional one for the generator, is known as the style ambiguity loss. Now for some implementation details. The dataset used to train the model was scraped from WikiArt. I happened to find an already scraped dataset while searching through GitHub, so I just repurposed it for this project. The architecture we used is a slight modification of DC-GAN. At the end of the day, we only needed to modify a few lines to use the style classification and style ambiguity objectives. Our development process started out with the smallest networks possible. We first trained the model using simple MNIST digits. That meant our input image was of size 28 by 28. We'd observe the model loss after a few thousand steps, and if something weird happened, like the discriminator loss dropping to 0, as is the case of the D-loss real graph on the right, we'd stop training, modify the architecture, then restart. In this specific case, we had to basically drop a layer of the discriminator. Once we got good results on MNIST, we retrained our training on scaled down images from WikiArt. We started out with images of size 64 by 64, retrained until we no longer had bugs, then moved on to the next scale. Eventually, we got to the final scale, 256 by 256, matching the resolution of the paper's results. When observing the loss curves, there's this weird bump of the generator loss that I've never seen in any other neural network losses before. I suspect that around 60,000 iterations, where this jump occurs, the classification loss begins to flatten out, giving the generator a chance to properly optimize the style ambiguity objective. Along the way of our re-implementation, we ended up deviating a few ways from the original paper. First, we implemented a few GAN hacks. For those of you who don't know, GAN hacks is a repo that basically outlines all the different changes you can make to your GAN to improve training and reduce a lot of the negative results that typically come with GANs. We particularly only implemented two of these hacks. First, we sampled our Z vectors on a hypersphere, and then additionally we used a replay buffer. However, we're not entirely sure whether a replay buffer actually positively impacted our model or not. Next, we were unable to replicate the batch size used in the paper. We were limited to a single GTX 1080 GPU, and thus could only fit 15 256 by 256 images into the VRAM. The paper lists that they actually used a batch size of 128. It's likely that they used distributed training, something that I didn't have a chance to implement. I also suspect that the authors used a slightly different dataset, particularly because we had no idea how they scraped the images or what the criteria they used to identify images for training. we basically sampled our data sets independently. It's likely that they scraped their images at a different time and using a different subset of WikiArt. They also didn't release the number of images used in this dataset, so it's not clear how to compare our results to theirs. Finally, we only trained our networks for 25 epochs, where the paper claims that they trained for 100 epochs. This is merely a limitation on time. It took us 5 days to train 25 epochs, so we're currently training the remaining 75 epochs. With all that, here are some results. Note that each one of these images is picked at a different step during the training process. Our most striking problem after training these networks was the issue of mode collapse. This picture shows the extent of the problem from our latest run. Each image comes from an independently and identically sampled input vector. Despite having 16 inputs, each image effectively maps to only one or two different images. The GIF from the very beginning avoids much of this problem, but still is imperfect, and you might see some repeated frames if you pay attention. I also hypothesized that the small batch size we used during training caused the network to learn in a very myopic fashion. Effectively, the network fits heavily to some subset of the data that it has looked at recently. I suspect that this is the reason the images sampled at different training steps have such high variation between them as well. Some future directions we're considering. First, we are currently implementing the WGAN GP loss as part of the training process. This loss came from a paper called Improved Training Using Wasserstein GANs, and it's kind of been the de facto state-of-the-art for many new GAN papers coming out since the publication of that paper. It seems like it would help us avoid mode collapse, and it also seems to generally be a good idea. The second direction we're considering incorporating is a new architecture that came out from NVIDIA in October. Known as progressive growing of GANs, this method basically trains one layer at a time and gradually adds more and more layers to a generator as well as the discriminator simultaneously. We suspect that this also might contribute to fighting mode collapse. If you're interested in trying this out for yourself, please check out the Github Repo. My collaborator and I are going to implement all of the changes proposed in future directions, hopefully over winter break. If you have any other questions, feel free to email me. Before I finish, I want to thank Junyan and Professor Evros. I've learned so much from this class, and I'm excited to keep using all that I've learned in the future.